too cold for bike, isn't it? All right, so let's get started. So we finished the second module last time. So as usual, your write-up is due within a week. So we are going to start the module 3, which is mostly about application. So I'm going to show you applications of what we learned in the last few classes on learning, and you see all of the components that we introduced in the previous classes in the following lectures, all the way to the end of module 3. So today I'm going to talk about discrete sequential models and general conditional random fields, CRF. So these figures should be familiar to you when you're talking about learning UGM. So we have a data. So we are assuming here that the data is given to us, and the structure of the model that we are going to explore are different kinds of graphical model, but we are assuming that the model is fixed, and our learning objective is maximum likelihood estimation. During the talk today, we are going to learn the parameters, but to learn the parameters, we see that the components of the inference are also involved. So today's lectures is mostly about conditional random field, and more specifically, we'll talk about part of speech tagging and some case studies on segmentation. So part of speech tagging in natural language processing, there are several models introduced for that, and we're going to discuss some of those hidden Markov model that I'm presuming that all of you guys have seen in your machine learning course. We're going to see a variation of that is a mixture of, it's basically a directed graphical model. It's called it's called maximum entropy Markov model. And we're going to see, we see that the MEMM has some issues that get fixed in CRF. And we're going to digress a little bit, talking about minimum risk-based estimator that changes the cost function a little bit, and a little bit of digression on more like a philosophical things on the generative versus discriminative models in general. And we'll end the class with the case study on the segmentation. So to set up the scenario, we are assuming that we are given a set of sentences, and somebody has spent time and tag those for us. Tag the word, the sentence for us. Like what is noun, what is verb, what is the rest of it. So our samples are pairs of X, the sentence, and the tagging. Now, we want to learn, we want to train a system that basically does this for us automatically. And the method that we are going to start would be hidden Markov. We're going to start with hidden Markov model and study the different aspects of that. So if you remember the factor graph, I think we discussed this, that is a form of representation of the graphical model on UGM and DGM, that each of these boxes represent the factors and circles represent random variables. So in this case, if you think about at the start, so always we are representing our data as a start of a sentence and end of the sentence, and between are the words. So our y0 is always the word start. So, and X are words and Y's are tags. This is just to set up. All right. So we talked about the factors, how the factors look like. In this case, our factors are binary between two random variables, so it's gonna be basically a set of tables. So because our y's are tags, so the set of factors is gonna be set of tags. So let's assume for simplicity we have only 4 tags, verb, noun, and the other 2. And here each of these factors is gonna be shared across all of these factors. So I'm assuming that we are using the same factor between this and this. The parameters are shared because there is no reason to assume that this is changing. We also have a factor between tag and a word that on the columns you see different kinds of the words in a dictionary, and on the rows you see different tags. So you can view it as a long vector of tags. Here I'm assuming there are only 4 tags for simplicity, and the number of this is going to be my rows, and my number of columns would be everybody in my dictionary, every word in my dictionary. That's the setup. We don't assume that this is learned, but I'm just giving you an example how it's going to look like. Look, I'm going to learn these tables, these factors. So now, as I said, we're going to reuse some of these factors because the factors between these two are shared. So I'm going to reuse the same factor between y1 and y2. I'm going to use it for y2 and y3. So I'm assuming that does not change as you go through the sentence. Yes?
So we have, like, let's say, click y1, y2, y2, y3. So
yeah.
So the set of factors essentially propagates all the way through the chain because of that. Like, if there's an overlap between.
What do you mean propagate?
Like, the same set of.
The same set of factors are
going to be. Like,
yes, the same.
And that is because the kids overlap. Like y1 and y2.
So I'm going to use. So this is a function, right? This is a function. And this is, so is this, right? I'm assuming that I'm using the same function for all of them because I just want to reduce the number of parameters. There's no reason to assume that the function f1 and f2 are different, right? Okay. So, so let's say, so at the end of the day, my factor graph is going to represent my joint distribution between factors and the words that I've seen. So here's a specific configuration of the tags and the words for a sentence which has 1, 2, 3, 5 letters. So time flies an arrow. So now I want to compute the joint density between them. So all I need to do is go and read the right entry in each of these tables. So help me with that. So the first one is noun, verb, P and D. So how can I write it down? So which elements I have to pick? So remember, this is a factor graph, right? So it should be multiplication of this, 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 and so on and so forth. Right? Just going forward. Which elements of these tables I have to read? What numbers? For the first one, tell me what should be the first one for the noun. 4. Why 4?
Time and
yeah, exactly. Should be this one, right? Okay. And then for the noun and a verb, I have to go and read this one, noun and a verb, right? And so on and so forth. So this would be, my factor graph would be multiplication of all of these numbers. Well, the problem that we have here is that it's supposed to be probability, and I'm just multiplying a bunch of positive numbers with each other. But remember that the Gibbs distribution has a normalizer. And so I realized that I have to normalize it. But basically, what was the normalizer? It's like normalizer was summing over all possible configuration and just dividing by that sum. Right? Okay. So there would be a normalizer, and then I get my probability. That is basically a quick review of what we talked last time about UGM factor graph and discrete annuality. All right. So these will give me the joint distribution between y and x's. Again, a reminder, each of these factors are not necessarily probability distribution. It's just, it tells us how a specific configuration of, let's say, n and n follows by n are likely. So here, if we think, so are like, corresponding to each other. So it's not that likely that a verb is followed by another verb. So this is why V followed by another V is not that likely, but it's really likely to have a noun followed by verb. So this is why that these numbers are not normalized yet. It's just unnormalized value, and Z basically helps us to normalize it, right? So it's like how much one state lacks the other state, but it's not necessarily normalized. They are not necessarily symmetric as well. So because the chance of having noun followed by verb is not the same as verb followed by noun, so that's obvious. But at the end, so that is basically the setup that we have. If I want to compare this MRF with the Bayesian network, remember that the difference between, if I can show both of them with the factor graph, but the difference between MRF and Bayesian network is that each of the factors were normalized. And this is why the learning with Bayesian network was way easier, because there was no term that combined merge them all together. And if I represent my graph, if my factor graph is going to represent a Bayesian network, each of the factors is going to be normalized, right? So it's normalized over columns or rows. I mean, of course you can see it, but hopefully you know why it's normalized over one, not the other, right? Why is it? Why this is column sum normalized, not row sum normalized. If I sum over rows, over columns, sums to 1, but not over rows. Why?
It's normalized in rows, not columns.
Right, so it's like 8, 1, 1 is 1, right? If I sum over the other side, it's not 1. Why? It's a Bayesian network representation, right? So it's representing, if this is y1, this is y2, is representing y2 condition on y1. So y2 represents columns, y1 represents rows here. So for this conditional probability, if I sum over y2 is sum to 1, there is no reason to sum. This is equal to 1. But if I change that to y1, it's not equal to 1, right? Okay. All right, so of course, if I have a Bayesian network, I don't need to worry about normalizing it. So, but if I have MRF, I have to worry about this normalization. So another thing that we're going to discuss today is a conditional random field. So the difference between modeling conditional distribution and the joint distribution is that so here, our graphical model, if I'm directly modeling conditional, I'm modeling this, but not this, right? It's not joint distribution of the tags and the words. I'm only representing the conditional, right? And the difference between these two graphs, I can represent both of them with the factor graph. The only difference is that it's, so if you compare this with the previous one, you see that this is gone, right? Because it is clamped. It is clamped to the observed value. So for each of these nouns, I'm going to represent those with whatever things whatever words that I've observed. So time is a noun. I'm going to focus on a noun, but not the rest of it. And if the fly is a verb, I'm going to focus on verb. So the states are clamped. So I'm not modeling p, x, and y. I'm not going to model this. I'm modeling p, y given x. So for me, x is fixed. I'm basically defining probability distribution over space of y's given x, given a specific configuration of x. I'm going to see that more often. So again, the form of factor graph is the same, but the meaning of the graph is different because one of them is modeling conditional, the other one is modeling joint distribution. So as I told you, the difference between that because I'm not directly modeling x's, I'm clamping the factors correspond to x to one value that I've observed, and it varies from one set of words in a sentence to another set of words in a sentence. Is that part clear? What is the difference between modeling conditional versus modeling a joint distribution? Okay. So, so as I said, in this case, because I don't care about modeling x, all I need to think about is modeling y given x, which, by the way, this is what we do all the time when we are doing regression, right? When we are doing regression, we are saying that I'm modeling py given x. I'm not modeling x. I just define a probability distribution over y. So in a regression, this is very simple case. So I'm representing that as x beta plus some epsilon. I'm not modeling x explicitly. I just define a noise for y. Here you can think of it as a fancier version of regression that y is not just a number. It can be a whole sequence. It can be multivariate distribution. So think of a function. Oops. Think of a function that get x and produce y, except that y is not a number, is a whole series, is a whole multivariate distribution over y. So my y is a fancier thing. Is the setup between modeling conditional and the fully generative model clear? Okay. So we have gone through forward and backward model in HMM a little bit last time. Although perhaps not with the same name, but we reviewed message passing. I want to make this connection that we talked about two general algorithms, sum product and max product. So remember that sum product was to compute some marginals, and max product was to compute maximum a posteriori or maximum assignment. And we said that these two are exactly the same, that the machinery is exactly the same, that except the difference between them is that in one of them we had sum, the other one is we applied the math, but we had the same mechanism for message passing and all that. Sum product message passing, sum product belief propagation in HMM, because it was invented before all of this, is called forward-backward algorithm. And if you are interested in maximum assignment probability, the algorithm that we introduced maybe more than a week ago, and a max product belief propagation is Viterbi algorithm. The only reason that this guy has a different name is that because for specific HMM, both Viterbi and backward introduced before sum product, but later on, people generalize it to a general graphical model, and we know that they're equivalent now. So to connect, so probably in your machine learning class, you heard those as a forward-backward algorithm and Viterbi algorithm, but I want to tell you that all you know about sum product and max product is the same algorithm if you apply it on HMM. But of course, the max product and sum product are more general. You can apply it in much more general cases. So in the following slides, I'm going to fill up this algorithm, this table for you, and by comparing different algorithms. So you already know from your previous class and also from message passing classes on how to compute marginal distribution, maximum assignment, or maximum posteriori distribution from HMM. I'm going to introduce two more models that are MEM and linear chain, and I'm going to compare those with HMM algorithm for pattern speech tagging. So to go back to the discussion that we have about conditional random field and the tagging problem that we have, I'm going to run it. I'm going to use this simple example. Let's say that somebody is giving you a sentence which has only 3 words: find preferred tags, and you want to tag this. So, well, if you just look at the verb find can be verb, find can be noun. And also, preferred can be adjective, can be the past tense of preferred. And similar for tags. Tags can be noun, can be a verb. So if you just look at the words, you cannot detect the tags correctly because there is ambiguity. So you have to put this in a context. So the models that we have, such as conditional random field and HMM and any other models that we're going to discuss today, helps us to not only look at the verb itself, but also put them into the context. So what we want to do is to find the joint probability distribution between y1, y2, and y3 at the same time. So if you only look at the verbs without accounting for the context, you're basically only accounting for these factors. So if you train a simple classifier that reads the word and produces a tag for you, it basically corresponds to only these factors. So the extra factors is to account for the context. So to tell you a little bit of background about how belief propagation comes into this context of using CRF for tagging, remember that, as I mentioned, the forward-backward algorithm that we had is just message passing algorithm. So we had a belief. So we are interested to compute the belief for each word, accounting for all of the words around it. So at the end of the message passing algorithm, when a random variable receives all of the forward messages and backward messages, he can multiply all of them together and form a belief that what other words around me thinks of me, right? So at the end of the day, form a belief that I'm more verb or I'm more adjective. And so how we did that? We did it through message passing. We had a message that's coming from all of the verbs, all of the words on the left side of it, and which here I'm representing it as alpha, and all of the information that we have on the right side of it, that here I'm representing as beta. And of course, we have to incorporate the word itself, so it's coming from preferred. So preferred overall, without thinking about the context, most of the time is verb, and sometimes is an adjective. But when you put that in the context, that changes the equation, and as you see, in this context, it changes the preference from being most of the time verb to be adjective in this case. So, and this is basically what we did through message passing. So what is the forward message passing algorithm? If you remember, we showed this, if you remember the example that I gave you back then, it was, we called it annoying fly. So you remember there was 3 doors, and in these 3 doors, there was the cheese, smelly cheese, and this fly was like going through all of that. And I told you this message passing can be represented as the state of the fly at this point multiplied by the transition algorithm. So it's a matrix vector multiplication. So when your states are discrete, message passing is nothing but a bunch of vector matrix multiplication. So forward would be, so if I'm assuming that, for example, the factors between y1 and y2 is shared, so this is the same factor as these factors, so you can view the message passing from right as right side multiplication, and message passing from left side multiplication. So again, every time that the message, the content of message was coming from the left side of it, and every time, so whenever the message is received by a node, it's multiplying by all of the messages received from the other node, and pass it to a factor. When a factor receives a message, it applies its belief about the surrounding and pass it through. Anybody remember what was the? So we had two sort of mechanism in this case that factors were treating the message differently than nodes. Do you remember what was the difference between the way that factors and nodes were treating the messages? So if you remember, so what is the structure of the belief network? It's a bipartite graph, right? On one side is the node, on one side is the factors, on one side is the nodes. And we said that if you remember, we had this graph. So these are my factors, and these are my nodes. So F1 is X1, X2, and when I'm doing message passing for all of the incoming, so if a node wants to send the messages that is received from F1 or all of the other factors, it has to multiply them all together and send it. This is all the node does. And the factors, it multiplies them all together, applies its own belief, which is its own table, sum over all of the other random variables that the other guy does not understand and send it. But overall, the forms were very similar. So, so this is basically the review of message passing. So, but in this specific example, just to be a little bit more clear, so here I'm representing this simple sentence, which has only 3 verbs. And each of these words can have 3 states, just for simplicity. So here I'm using ellipsoid to represent all possible states of this algorithm, of this probability distribution. So I'm presuming that only possibilities that we have in this graph is verb, noun, adjective, just to plot it in an easier way. So you can view as a message passing. So remember, this is the entire thing is a random variable, but each of these triangles are the state inside of this random variables. So you can view this message passing as a path that goes through the states. So how did it work? So let's say that for a specific configuration, find is a verb, prefer is an adjective, and tag is a noun. We start from a start state and pass the message between them. So every time we pass through a factor, that factor applies belief and send the message to the next state. So here I'm just showing, of course, we are not going to do it this way and enumerating over all of these possible states because it's computationally insane. But I'm just showing you if I would have done it, you can view it, you can view this probability of this configuration as probability of a path. So probability distribution of the find being verb, prefer being adjective, and tag being a noun is probability distribution of this specific path. So, and how we compute this probability distribution? We compute this probability distribution by multiplying these unnormalized factors with these 7 unnormalized factors. Why do I see 7? Because we have 7 factors, right? 1, 2, 3, 4, 5, 6, 7, right? Every time we pass through a path, that the factors applies belief on it and pass it through, right? And then, of course, we have to normalize it, and let's assume that somebody has given us that normalize that. But the specific configuration of verb, noun, and an adjective is basically distribution over this path. So, of course, in this setting, I'll get back to it. So in this setting, this path has the highest probability, but if you don't know the prior, you have to compute all of the paths. Of course, if you want to compute all of this path in a naive way, is going to be exponential, but we introduce this dynamic programming type of thing, which basically call it message passing, to compute this efficiently. Yes, you have a question?
You said when you calculate using the factors, you need to marginalize. The reason there's no marginalizing here is that...
Oh, there's a marginalization. There's a z here, right?
But you said every time a factor is included, it needs to
be
marginalized.
No. You apply the marginalization at the end, right? If you have a Bayesian network, there's no marginalization. Z is equal to 1, right? For a given UGM, there is a marginalization that you somehow manage to compute, which is basically an inference algorithm. But you have it somewhere. But here I'm giving you intuitively how it works. Every time that you pass through a factor, that factor will influence your path, which here, if you go from start to a verb, the first factor's element 0, 1 applies its belief on it. Next time that you pass through verb to adjective, you're going to have the effect of verb adjective. Next time that you go from adjective to noun, next factor is going to influence. And every time also, the content of its verb applies belief on it. But of course, if you just multiply the factors, you're not going to get probability. So you have to divide this by 1 over z. This is our Gibbs distribution, right? Remember, the Gibbs distribution was 1 over z theta, sum over all of the clicks, click potential, xc. That was our joint distribution. These are the factors. Make sense? Okay. Of course, this is one path, but there are all other possibilities of the path. For example, what if A is an adjective? It's very unlikely. But what if A is an adjective, and then the next one would be adjective 2, which is very, very unlikely. But anyways, if you don't know a priori the best optimal path between them, you have to go through all of this. But the message passing is basically a way to do this in an efficient way. So to give you an idea of what marginal probability was, so for example, if you want if you want to compute what is the probability, this marginal probability distribution of y2 equal to a, that equivalents to setting y2 equal to a and summing over all of the paths. So what are the other possibilities of reaching a? So maybe the previous one is verb, maybe previous one is noun, but I have to find all of the paths that goes through this. So if you think about path, if you want to have another intuition of what marginalization does, is basically computing the joint distribution of all of those was, as I told you in the previous slide, was equivalent of computing the best path. Computing the marginal equals to computing sum of all paths that passes through specific states. And similarly, for example, if I want to compute p equal y2 equal to noun, so I have to go through all of these paths that goes through noun. We are not going to do that. We didn't do this naively, but I want to give you an intuition. If you think about path, that's what marginal means. And similarly for verbs. So, but of course, as I told you, if you want to do it naively, you have to enumerate over all possible verbs. And this is exponential. This is so expensive. So we had this message passing algorithm that computes all of the message that goes from left and goes from right. So, for example, if I want to compute the marginal of y2 being noun, I have to receive all of the possible paths that passes through noun, which I can show it as alpha 2 now, the weight of all of these path prefixes. And to compute this, I don't need to actually enumerate this path, and this path. The message passing is a dynamic programming to do that. So all I need to do is sum over all of these paths. And similarly for beta 1. So the general idea at the end is as follows, that all you care about is sum of all of these paths. you don't need to have A, B, and C. All you need to do is computing A plus B plus C. And similarly for the message that's coming from the other side. You want to know X, Y, and Z. If somehow I have an algorithm that gives you the sum, you don't care about having X and Y and Z explicitly. So at the end, if you want to compute AX, AY, AZ, and BX, so this system, you only need to compute these two together. So the naive way of computing this sum is having access to A, B, C, X, Y, and Z explicitly and doing this multiplication. But if I can write this multiplication as A, B, C multiplied by X, Y, Z, I don't need to give you X, Y, and Z explicitly. I have to come up with an algorithm, which is basically dynamic programming or message passing, that gives you this sum and this sum. You just multiply them together. The result would be the same. And this is basically the underlying trick of what we did last time, and we call it message passing. Instead of enumerating all of these possible paths, which is exponential, instead of all you care about is this sum. I'm going to give you the sum. Make sense? Is the setup like why this setup? So I think at the beginning when I was trying to motivate this for you, I told you that, well, you can put the sum outside and enumerate. So remember that all of this marginalization, we had a bunch of sums and something here, right? So if you want to enumerate all of the possibilities in sum is exponential, because if this is k, and this is k, if I have, I don't know, m of these is going to k to the power of m. But the trick was that the form of the function that we have here was such that it was decomposable, and we were able to push each of these sum inside and compute this. This is another way of saying the same thing. Okay. So at the end, computing marginals was basically computing all of the messages that I received from left, from right, and of course the verbs that I observed, in this case prefer, multiplying them all together and normalizing it. So I have all of the message from left, which is I call them alpha for noun for this specific configuration. And if I want to compute the probability of Py2 equal to noun, I have to multiply the belief of all of the nodes on my left side that think that I am noun. They think that I'm noun. Multiply by all of the messages that I receive from my right side that think that I'm noun. And basically consult with the verbs that I am, which is preferred, which here I'm representing as this, and multiply it together and normalize, and that's my marginal. And similarly for the other one, if we want to compute the probability of Py2 being verb, all of the message, all of the belief of the other words in a sentence that thinks I'm a verb, right side that thinks I'm a verb, and consult with my verb and compute it. So this basically summarizes what we did in the form of hidden Markov model. So in hidden Markov, what is hidden? The tags are hidden. They're not observed. The verbs are observed. And we have a Bayesian network that starts from the start tag the sentence, and the joint distribution can be written as emission probability and the transition probability, right? And it's also obvious from our Bayesian network. So, but there are issues with this model. So, first of all, remember that this is, so here what I'm doing, here I'm modeling both X and Y at the same time. But if somebody tells you that, all I care about is tagging, I don't care about generating new sentence. I give you a sentence and you tag it for me. I don't ask you to make a new sentence for me, just tag it. So why should I model the joint distribution? It seems that if your objective is tagging, you're better off modeling y given x. But you just save some effort. You're not interested to generate new sentences. You're only interested to generate new tags. So why not modeling this directly? So it seems that HMM in this case is wasting some effort. So another thing which is important is that okay, so I've already said that. So as I told you, the HMM modeling the joint distribution of the tags in a sentence. But if all you care about is tagging, you're only interested in this. So why not having another model that does that? Another thing which is important here is that in HMM, although we are collecting all of the information from all of the sentence on the left and on the right, the emission probability only sees the words on it, right? So if I'm Y2, I see a summary information from my other verbs through the message that I receive from the left, and all of the message that I receive from the right, but I don't see those verbs. The only verbs that I see is X2, right? Wouldn't be that better to incorporate all of those information? Can I provide an access to those? So maybe I have to introduce another arrow, or maybe so somehow I wanted to have access to those. So that improves the result, because sometimes you have to. HMM only looks at the local information. Maybe you want to see that I might be a verb if the next word that comes after me start with capital letter. So maybe I say I like flowers, or I said the book smells like a flower. So this like and that like, the one of these verbs, the other one isn't. So, or it smells like the name of the brand of the perfume. So if the name of the brand of the perfume, it usually starts with capital. So I want to see that if I want to tag the word like, I want to see the word next to it. That might have some information for me. So an HMM does not account for that. So what's another way? So what if we do this? Instead of thinking causally that there is a tag that produces a verb, I'm going to reverse the direction and go from the entire sentence to all of these tags. Remember that. So if you think causally, this makes more sense than this, because here the arrows here are representing are going the other side. But I want you to pay attention that arrows does not always have a causal meaning. It's just conditional. It's just conditional probability distribution. So how am I going to model it? So this is one way of modeling. For each tag, so if I have a word of the sentence, find preferred tag. This is my entire x. So here I'm representing it as x over y. I'm going to provide the entire sentence to each of the tags. So how can I come up with the distribution? So I'm going to reverse the arrow and view this as a regression. So the way it works is that I'm going to extract some features from pair of the tags next to each other, and also incorporate sentence and somehow come up with some features that we'll discuss some of those later, and normalize it. Right? So the result would be still is a Bayesian graphical model, is a Bayesian network, but is multiplication of bunch of factors. So you can view it as sort of regression between pairs of random variables, between these pairs and whatever they observed, between these pairs and whatever they observed. So each of those is a regression. And also notice that because each of those are regression, there is no overall normalizer because I'm normalizing each of these pairs independently. Right? So if you compare it with Bayesian, if HMM, the Z was equal to 1 because each of these was actual probability. Here, what I'm showing here is that I'm viewing each of the pairs of y1, y2 as a regression and normalize locally. Right? It's easier to normalize because let's say that if you want to tag them, if you have, let's say, 5 states, I have to enumerate over 5 by 5. Right? Z is easy to compute. So basically, this is the idea of so-called maximum entropy Markov models, or MEMM. So instead of providing the local information to each of the tags, it's going to provide the entire sentence to each of the tags. And is going to normalize each pairs of the tags and have the following form. I have to mention that this arrow right now does not have any causal meaning because you're reversing the direction, and if you think causally, that doesn't make sense. Nevertheless, as I said, arrows does not necessarily have a causal meaning. It's just conditional independence. So this is an example of a discriminative model because here I'm not modeling P, Y, X. I'm just modeling Y. So there is no way I cannot use this model to generate new sentences. But I only care about tagging. So why not going for discriminative model? So this model, the learning objective is to learn Py given X, learn the parameters of Py given X. But this model also has some shortcomings. So let me give you an example. So let's say that I have a sentence that has 5 words in it, and each of these tags can take 5 states. So first word, second word, third, and fourth. And each of those have 5 states, like, I don't know, like noun, verb, adjective, so on and so forth. Okay. So I start from observation 1, word 1. And remember, in MEM, I was modeling PY1, PY2, all the sentence. Remember this? Remember this, like I was modeling the pair of this, right? The transition probability of going through, let's say, tag verb, starting from noun, given all the sentence, right? So every time is a probability, is normalized. So let's say that I have somehow, during my optimization, I went to this specific state. So I'm showing you as a path. Remember that I said that you can view this as a path. So it seems that the first word preferred most of the time from going from state 1 to state 2 of the second one, right? Because this is 0.6, this is 0.4, right? So it's more like it. If I ask about the first word, it prefers to go from a state 1 to always go to state 2. And the rest of them are 0. And then from a state 2, this is the maximum. So it stays in the state 2 and state 2. Right? This is the path. If I start from state 1, most of the time goes from state 1 to state 2. There is the other probabilities are 0 because this sums to 1. And the state is state 2. But this is not the optimal path. So let's see why it's not an optimal path. So let's start another path. If I compute the path of going from state 1 and going all the way with the state 1, is going to be multiplication of this, this, and this. So the probability is going to be 0.9. Another path. So going from state 2, the probability of staying at the state 2 is 0.18. Going from a state 1 to a state 2, and then going from 1 and 2 is so on and so forth. So if you compute this, the probability of staying at the state 1 is more than probability of what state 1 prefers. So every time the state 1 prefers to go, most of the time prefer to go state 2, but if you compute these probabilities, 0.6, 0.3, 0.3, it's less than this. So if your objective is to find the optimal tagging, which basically boils down to find the best path, this is not a good model because it has a bias with respect to state, because it only makes a decision locally. It doesn't account the sum of the others. So, and this is what is called label bias in MEM model. So, although the most likely path or the most likely tagging would be a state 1, a state 1, a state 1, a state 1, because the decisions are local and does not account the other states, you will end up with a distribution that is less likely. If you multiply them with each other, it's going to be 0.9 multiplied by 0.6, which is less than this, less than this one, less than this one. So the local decision is not optimal. Yes?
Is this true for HMM as well?
This is true for HMM as well. Yes. And the reason it is true because each of these factors are locally normalized. That's exactly true. So how can I do this? How can I? So because each of these decisions are locally normalized, and if I ask the state 1, where do you want to go to? You say state 2 all the times, right? So I have to somehow break this and say that no, you have to look into other models as well. So one way to do that is say that don't be normalized. At the end, if I want to find the best path, I want to remove this normalization and make all of these states dependent on each other so that my path will be optimal path. So the remedy to that is actually very simple. Instead of using local probability, use local potential, which is not normalized. So I remove the arrows basically between the states. So I go from this model to this model. See the difference? So I remove the arrows from y1 to y2. The problem that it introduced is that, remember, in MEM, each of the factors were normalized. But here, the normalization goes outside. So I pay the cost of computing non-local normalizer, which is harder, because I want to get the best path. So the resulting model is called linear chain CRF, which is basically partly UGM, partly Bayesian network. So it has some directed arrows and some undirected arrows. So I remove the directionality from here because I want to have this path to be dependent on each other. I don't want them to make a local decision. But I'm fine with going through regression from X to each of these Y's. And this is basically local chain. So similar to MEM, CRF is also a discriminative model. It does not model X. It's just a better model for joint distribution. And the other difference that I told you is that the factors are not normalized. As I told you, so the factors are not normalized. So this normalization goes outside. Yes?
I don't remember we discussed graphs that have direct relations and undirected.
No, we didn't discuss, but that's the same. You know all of the material. So I can do whatever I want. I don't have to have, I don't need to use only direct or indirect graph. The UGM is very general, right? So all I need to do is that if I have a graph that partially normalized and partially arrowed, partially not. So what is the general graph? So still I can compute the joint distribution as multiplication of the factors. But because I have some I have some connectivities or factors that are not normalized, at the end I have to normalize. But the general idea applies. So if I have something like this, so it's going to be x1, x2, x3. The joint distribution of x1, x2, x3 is going to be px1, px2, px3. If I have, let's say that I have another network that goes like this, I can write it as what? Somebody help. Px2 given x1, yes? This is not arrow 2, so so there is some factor between x2 and x3, and there is another factor that between x1 and x3, right? And a normalizer, exactly.
For the 2 out of 3, right?
No, but you need to have a normalizer that depends on everybody. As soon as you make one of them unnormalized,
yeah. So in the computation of the normalizing factor, we take into account all 3, not just the 2 that show affinity.
Yeah. But if you think of it as a factor, this is still a factor. I call this side 1, side 2. I can call it side 3. So the notion of factors was that it's just not normalized. But if you want to put something normalized, okay. Make sense? All right. So what is the distribution of this joint distribution? Remember, so here I'm showing this as a conditional random field. So I'm modeling py given x. I'm not modeling x. So if I write this as a factor graph, it's going to be some normalizer, bunch of terms that has a pairwise, and a term that goes from x to y. So I just write it as an exponential, but I could have write it as a non-exponential, but it's always true. So it's like I can write it as a pair of yi minus 1 x and call the factors on OK. So this is basically x of that is this term. Okay? Now, if I merge them all together, I'm going to have a form like this, that I'm going to have a linear term that goes from x to y, and another term that goes from x to the pairs. So now my question is that, is it still exponential family? What do you think? Can I write it as an exponential family? Why?
Sum of exponentials is not necessarily exponential.
But what do you mean sum of the exponential family?
You're summing over y.
If I have a random variable x, a random variable y, which are exponential family, if I sum them up, it is not necessarily exponential family. But that's not the sum of the exponential family.
So you're summing over y down there.
Right, but I'm not modeling, I'm just modeling y. X is covariant, is some feature, external information. I can write, remember how the exponential family look like. Exponential family look like some parameters, sufficient statistic, normalize, log partition, and some hx. Okay, so I can do that. I can say lambda mu transpose f g. Right? I haven't left the exponential family yet. So the first term is called unary term because it has only term of y1, and the second term is called binary term because it has a pairs of y's. And you see that again and again in the context of CRF, both for imaging and for other type of things. And the other difference here is that, so in exponential family, we had a z that depends on theta, right? Here our z depends on x because it's like external information. But remember, we are modeling py given x. This is probability distribution with respect to y. And x is just some external information.
So you can be treated as a parameter.
Yeah, it's like except that it's not the parameters because you're not playing with it, but it's just external information. If you change that external information, your normalization also changes. Make sense? Okay. What if I want to do fancier things? So I want to say instead of pairwise. So I call this term binary, right? Because it has y1 and y2 which are next to each other. What if I want to have dependencies between y1 and y minus 2? What should I do? How does this form change? Yes.
Didn't you already do this to model the more than a pairwise dependency? Like you take away the
No, but if you
arrows
look at
to-
the terms, all of my terms look like something that has only some things that has only y1, yi with x, and something that has yi and yi minus 1 x, right? What if I want to have another set of dependencies? I want to have something that yi minus 2, which is equivalent of connecting with another arrow. All I need to do is just like add extra features, right? So I had lambda transpose f yi minus 1 x. I can have, I don't know, new transpose, let's call this h, yi minus 1, yi minus 2 x, and so on and so forth. It's just introducing dependencies is as simple as that. Computing that would be a whole different story. It might be difficult, but if you want to introduce more dependencies, it's just simple. Just come up with the features of triplets, and you can do it. So, to show you how this computation will look like, so remember the likelihood of MRF. So the data that we have for MRF is just I have a Bayesian, an undirected graphical model, and back then I assumed that everything was observed. So it's basically the observation that I have for each of these x, 1 through x. So here I'm using super index as a new sample. So this x is basically x1 through x4. So this was my MRF. So probability distribution of that was basically x condition on theta was exponential family, right? So I can write this as a normalizer and sum of the factors. Sorry, multiplication of the factors. Right? Do you remember this form? Right? Now, if you have a CRF, now for a CRF, I have something like this. Some forms like this, that there are a set of them that are observed, called these x's, let's say, x1, x2, x3, and a set of them that are unobserved and I want to estimate. So the data set that I have comes as a pair of xy's. So the probability density of that would be, I'm interested in computing p given x. So my z depends on the parameters and also x. And my factors are basically these joint factors of y's and x's. So if you compare these two, see that my factors has xy, here while it has only x's, and the normalizer only depends on the parameters, while normalizer and CRF depends on parameter and the observed covariance. So how does the likelihood of this look like? I mean, of course, the likelihood of that, if I so the likelihood of MRF would be log of, so the log with respect to theta and data is going to be log of px comma theta is going to be sum over samples, sum over factors, log of p factor c, xc, and theta minus log partition function. Right? This was the MRF that you have seen before last week. For the CRF, would be 1 over n samples, factors, pairs of factors and observation, and a log of theta and x's. This is just log of these substituting data in. All right. So now, what is a derivative? So do you remember the form of derivative of the log likelihood? Do you remember the form of the derivative of the log likelihood with respect to theta for MRF? It shows up as two expectations, right? Some empirical minus the actual. Do you remember how it looks like? Anybody? No? No. So if I take a derivative with respect to this, would be if I, let's say that if each of these theta c's are independent, if I take a derivative with respect to c, only this term shows up. So I'm going to have only this term. And the log partition number was expectation, right? It was expectation with respect to, so here I'm writing things for CRF for you. So C log partition of, so let me write this as a feature. So I'm gonna write this as, I'm gonna use the featureization now. So X C, Y, C, and I'm going to use this as some theta C transpose this, right? Okay. So the log of that would be this. It's going to be features of XC minus YC. So to compute, this is, and again, so let me write it as a form of features. If I write it as a form of features, it's going to be YN. F XC YC. So this was empirical mean minus the actual mean that you have already seen before. And to compute this mean, you have to compute these marginals. So you need an inference. This is basically from last week. Learning the parameters of fully observed UGM. So that the game is the same, except that the features look different and has X in it. Everything's the same. Do people remember any of that? Or not yet? Maybe you'll remember when you start doing homework. Okay. So to compare these three methods, HMM, just do the counting. It's very simple to do the learning on that because everything was normalized, and all you needed to do was basically to compute the state of y. You have to go and count it, and it was the form of the theta was maximum likely destination. in MEMM, we have to use the gradients, but it has the gradient, it has the bias of the labels. Linear chain CRF doesn't have the problem, but because it's removing the normalization, makes everything dependent, but it has some issues. It's difficult to learn because every time that you want to make a gradient, you have to do inference, and that's a problem. Well, it's difficult, not a problem. So we keep showing you this f, x, y, and like it seems a feature. It's a feature, but I haven't told you how to come up with the features. Like, what is this function? So in the following, I'm going to give you some ideas how to build these features. So if you want to do part of speech tagging, so one obvious would be, so if these features were a function of x, which is the word that you see, and a tag. So it would be very obvious to say that how many times I've seen the word. So I go over my corpus, my dictionary, or whatever that I'm using, how many times I've seen the verb like showing up as a plural. That could be one feature. Another, so you can view this count as a log emission probability in HMM. Although like here nothing is normalized, but here you can design it that way. Another idea would be, well, how many times the tag p even possible? Maybe in English we don't use this. I mean, of course we always have verb, I guess. So a sentence without verb doesn't make sense, but we don't use all of the possible tags. So some of the tags are less likely. So you can think of it as a prior probability of a word. Another idea would be count of how many times we see p in the middle of the sentence. Is it possible to start the sentence with let's say that how many times is possible to start a sentence with a noun? How many times is possible to start a sentence with adjective? I guess it's not very likely, but I haven't seen it in a sentence starting with an adjective. It's always noun.
No.
So
Beautiful people dance.
good. So then it's less. It's not exactly 0. So so you can use this as your as some sort of like how likely it is that you design it as a feature, and you can also use the pairs of the verb. So remember my feature. The other feature that I had was look like yi minus y and x. So if this is yi minus 1, this is yi. So how many times we see verb, and so you can use these recipes to design features. So, and of course, this is the laundry list of the way that you can do this, and then you can combine all of this with some sort of like a template. So you can say that. Okay, so I'm just like having more laundry list. And as I told you, if you want to have more dependencies, if you want to have a features that is dependent on yi minus 1, yi minus 2, you can come up with triplets instead of doubles. And at the end, you can combine these features with some sort of like a template. And this basically gives you a way that you can build easily thousands of features for each of these parameters. So your f can be 1,000 dimensional. So how you can do this, you can say that how many times I have seen verb followed by a suffix w. So, and count it over your corpus, and that here goes. It's going to be your new features that you have. So you have to go and engineer all of these features. So I'm going to pause here and give you that. Well, here to design this sufficient statistic, we have to put a lot of effort designing good features. So here, hopefully give you some appreciation for methods that are based on deep learning that hopefully can be used as a feature in this case. You can use your deep learning method to give you a feature and learn things jointly. But of course, one way to do that is to hand engineer the features. Okay, so I'm going to skip that because I haven't talked about the imaging yet. So to compare the generative model and discriminative model, so I'm going to give you a graph. So this is some studies done by Liang and Jordan back in 2008. They applied part of speech tagging on 2 data sets. One was a real data set from Penn tree banks, and the other one was artificially created data set using HMM, if you compare the accuracy of these two for the data set that are synthesized, of course HMM does better. But HMM necessarily is not a good idea for a real data set. So these, hopefully, the take-home message of that is that if the model is misspecified, most of the time discriminative models are better. And in reality, models are misspecified. You don't have very explicit model of the world. So if your objective is to do a specific task, such as tagging, go for conditional model. Because unless your fully generative models are not exact, the true representation of the world is not going to work better. But if the model is close to the truth, you see that HMM does better. To compare HMM and MEM and CMRF, these are two different error and auto vocabulary error, just viewed as two different measures, two different evaluation measures. So you can't really make a decision between HMM, MEM, and CRF on a real data set, but if you incorporate additional spell checking, usually CRF performs better than HMM, and CRF performs better than MEM, which are here I'm represented as CRF plus that incorporates spelling. And they're both way better than HMM. So this is basically another take-home message that for real data, if you design good features, go with conditional model. Also, in all of these, I told you things about using maximum likelihood estimation, but sometimes there are discrepancies between what you are evaluated with and what you are training. So using maximum likelihood estimation is not necessarily the best thing. Because it depends. If your goal is to, I don't know, beat the benchmark, and the benchmark is using specific loss function, why not using that loss function? So a way to do that is basically using minimum base risk estimator. The idea is as this. The idea is very simple. You want to fit a model of P y given x, but not all of your y's, not all of the configurations are equally scored. For example, if I have a sentence and it might be more, I may have to pay more penalty to tag the word, let's say, like, as an adjective than tagging it incorrectly as a verb, because that's my measurement criteria. So let's say that that's a benchmark that you want to beat. So that benchmark gives you a risk, and you have to incorporate that risk. So how can we do that? So the idea is this: we instead of computing the log of Py given x, we compute the expectation of your loss that's coming from your domain. So I'll give you some examples of that. So this is basically what you have observed in your data set, and this is what you estimate. So you basically train a model. You say that, like, let's say that for my current iteration, theta equal to t. So I compute this expectation that is coming from so somebody has given me, this is the criteria that you have to optimize if you want to beat that benchmark. So I have to optimize my y so that my risk is minimized. That's called a decoder, or I think people call it, expected loss decoder. So what are the examples of this? So let's say that if your criteria is Hamming distance, you have to get every single tag right, unless there is no, you will be penalized. Then the equivalent loss function would be my prediction, and the ground truth should be exactly the same. Otherwise, the loss, I'm not going to give you anything positive. Then computing that expectation to compute that the decoder would be equivalent of finding the best y. So your decoder would be find the y. So if I compute this, my decoder would be minimizing this, which would be what? Like maximizing this. So at every step of the decoder, I'm doing a map estimator. Does that make sense? Because if I'm minimizing this, I'm basically maximizing this guy, right? I'm searching over all y's that gives me the maximum value of this. So if your loss function is, if the loss function you're evaluating with is a Hamming distance, is equivalent of doing map estimation in every iteration. Here's another one. So you may say that, yeah, so overall should be, you don't have to get all of the verbs, but marginally you have to be correct. So my loss function that the loss function that you'll be evaluated with would be not getting everything right, but getting most of the things right. Right? So if I have a sentence and I have a tagging of VP, I don't know, N, I'll get, and the truth is VP, I don't know, something in P. So I get correct, correct, incorrect. Right? So this is another loss. This is a Hamming loss. So this would be sum over the marginal. So the equivalent of that would be for each of the tags, you have to compute the marginals and sum them up. So what is the difference between them is that when you have explicit loss function, use that loss function and then take a gradient. And most of the time that boils down, you have to do inference anyway because all of those boils down to a specific kind of inference, but that would be the case. I don't think I have time to go over the segmentation and the imaging application, but I guess you guys can over it yourself. Thank you.